Well, hello, friends. Today we're going to enable a safety mechanism in the kernel of Serenity OS, and it's called the WP bit. And it's this bit in the control registers of the CPU that says that, well, I'm not going to find it here, but I'm just going to tell you what it is. It's a bit that says that even if you're running in the highest privilege mode, so in kernel mode, you still can't write to read-only memory. Because currently, by default, on x86, you are allowed, if you are the kernel, so if you're running in ring 0, you're allowed to write to read-only memory. And the paging, or the MMU, just ignores the write access bit of page tables. But if we enable that bit, we will start getting page faults in the kernel if we, in the kernel, try to write to read-only memory. And this is something that I didn't enable early on in Serenity because I didn't quite know how everything worked and how to get all the paging stuff to work the way I wanted. And I think I turned it on at some point and I got like a million crashes, and I didn't want to deal with it, so I just let it be off. So it's been possible to write to read-only memory in the kernel this whole time. But today we are going to turn that bit on again and then deal with whatever happens and then come out of it with a kernel that cannot write to read-only memory, which hopefully will allow us to catch bugs in the future, because it would be a bug to write somewhere that you should only read. So let me just find, no, not whip. So what is the thing? Write protect bit 16 of CR0. Right. It inhibits supervisor level procedures from writing to read-only pages. When clear, you are allowed to write to read-only pages. So we want to use this. So let's turn it on. And I think we can turn it on when we turn on paging, because that's the moment it becomes relevant. Because until we have page tables, it doesn't matter. If it doesn't matter. So we turn on paging here at the end of Memory Manager Initialize. If you watched my video on the virtual memory system of Serenity, then maybe you remember a little bit of this. So here is where we actually flip the paging enable bit, right here in the CR0 register. So it said that it's the bit 16 of that register, so that would be 116. I knew that. So we just put a 1 right here. And we will now also be turning on the write protect bit. And the kernel will start crashing if we write to read-only memory. By the way, check out this new build system that JCS made. It's super duper sweet. There's a big makefile in the root of the project that knows how to build all of the sub-projects. And like if I change a header file somewhere, then a make in the root can now only rebuild the stuff that actually depended on that header file. It's super duper sweet. Really excited about that. So I just wanted to mention it. But anyway, let's get back to the kernel. So let's run now with this turned on. And of course we crash right away, because I don't know what I was expecting, right? This is exactly what we were expecting. So we have a page fault, write to address this address, and then we completely kill the kernel because we don't know how to deal with a crash in ring 0. So the fix, of course, is going to be to not trigger this page fault. So it's in exec. So when we load an elf binary, and presumably this is just trying to read from the elf binary, I bet you that if we go to do exec, we'll find that we are mapping the elf into memory here, prot read. So we're mapping the elf of every program, we map it prot read. So what if we just map it prot write? And then just go about our day. And then we crash a bit later. Okay. So we made it a little bit further. Now we are crashing in an inode fault. So we're getting a page fault in some area that is backed by an inode, and we cannot write to it. And I bet you that it's this one right here. So what's the address? 806A000. That is 806. It's in here. Yeah. This is 804 through 808, and we were right in the middle in 806. So definitely crashing in there. It would be kind of cool actually if we would show like a little red star or something here next to the region that you actually crashed in, or if it was in between two regions, you could show the star somehow. It'd be a cool little feature of the crash dump. Anyway, so we can't write to this because it's mapped read and execute only. Fine. So the correct solution is, so what's happening here is that we map the system server binary. We map it read write, which actually we should remove the write bit after we have loaded the elf. So we'll say set writable false, and that should turn this into R only, even though we still crash. Yeah, so we're good. So now when we load a program, it's writable by the kernel during load, but we never actually transfer control to the program before removing write access to the code. It's pretty good. And okay, yeah, that's fine. And then now the next problem is, so we're mapping this segment here, right? And we're just mapping these based on what the elf binary is telling us. So in this case, it's the system server, which is here, and the elf header is telling us to load these two program segments. This one here is read execute, and this one is read write. So the read execute segment is this one, and we have to be able to write to it while we're loading it, but it's lazy loaded, so we don't actually load the pages from the disk until you read from them the first time, which happens in the form of a page fault. So that's what we're getting here, right? We get a page fault, and then we go into the inode fault handler, and then it cascades and goes into another inode fault handler because I guess it's trying to symbolicate the crash, and it's not able to do that either. But anyway, we have to be able to write to this in the inode fault handler. So handle inode fault. The way that we fault and file backed region is take the lock, see if there was a race and somebody already paged it in. Otherwise, we read the bytes from the file system into a page buffer here on the stack, potentially pad it with zeros, and then we turn off interrupts and allocate a physical page and map that physical page into the region, and then copy the stack buffer into the destination, which is the newly allocated page. We map it into the process address space before memcopying. So because we're doing it this way, that means that when we map it here, it uses the actual protection of the region that we're mapping it into. So we could do something like was writable is writable, and then we could do like set writable false, and then after we've done the memcopy, we could do set writable was writable, and then remap the page again. So this is really ugly, but would it work? Not quite. Also, we crashed again in the elf flutter because why? Did I get a little too excited with revoking that writable thing? Okay, fine, let's leave it writable. Am I even changing the kernel? Okay, elf image, prot read, prot write. I would like to, wait, what am I doing wrong now? It was working before. We got further than this before. Is it because I'm screwed it up here now? Handle inode fault. So what if we just undo these changes? Now we get farther. Okay. So I guess the loading code of the exec is actually using that. So if we set writable after, we still get to here. Okay. But anyway, what the heck was I doing wrong in inode fault then? Setting it to writable false. Wait a minute. I have to set it to true, otherwise I'm going to fault there. Jeez. Okay, that's stupid. Because the whole point is that I need to be able to write it temporarily. Oh, okay. Here we are. That's enough to boot. Can we do some stuff? Can we run Doom? I don't have Doom. Okay. Seems like we're able to actually run and do stuff. So I hate this code now. This is super ugly because we are setting the permission to writable once and then unsetting it to the previous value, which is so stinky. And I think we should just map it somewhere temporarily. So we can use this hack in the kernel. It's called quick map, which is fine to use if interrupts are disabled, and we have disabled interrupts here. So quick mapping gives us, it maps a physical page at a known address. It's the same address every time, and it's just a way to map a physical page into memory so that you can copy something into it, and then immediately afterwards we unquick map it, like that. And then we don't have to actually touch these bits. We can just leave it alone. I think that's fine. It's a little bit ugly, but at the same time, it's also a little bit nice. Well, this was pleasantly easy. Can we load some website? Do a little bit of this and that. I can't really open any of these links because they're all HTTPS. Ah, crash. Why did we crash even? I guess we can't handle a failed download. Oh, that's an entirely different problem. So these changes are pretty interesting though. We should definitely take them. So what did we have to do here to make this work? And it's fascinating that it just works basically with those minor modifications. I wonder if something breaks from this. That crashes, but that's a known crash. Piano kills the kernel when you exit piano. I guess I just wish that there would be something that would crash so that we could look at it. This works. Can I build? There's some problem, but I don't think that's related to this. We didn't crash the kernel, because the whole point now is that we would crash the kernel if something goes wrong. We would get this big fat page fault, stack trace, and it seems like we're not getting any more. Damn, I was postponing this, dealing with this for so long. And all right, fine, I guess it works. Cool. Well, it's going to be an easy patch for today then. So we'll just say, we'll review the changes. So here we turn on the write protect bit on startup after initializing the page tables and stuff. And then in exec, when we initially load a program to run it, while we're loading it, we have to keep the memory writable, because during load we're reading from the disk and writing it into memory. So this is just for like writing the ELF image into memory. We have to be able to write to that memory. That makes some amount of sense, but at the same time, do I actually need this? Because now I'm wondering, prot write. What if I just don't have it? Would it be enough that the page fault handler uses a quick map to make it writable? It seems like that's enough. So then we can avoid doing it this way, keeping it even simpler. Because I didn't really super like the fact that we had to make the memory writable during ELF load. And it seems like we don't even need to do that. Let's look at something. Audio menu applet. That's this guy right here. This is the ELF loading staging region or whatever. You can see here it actually has a K, which means that it's kernel only, so we couldn't access this from user space even if we wanted to. Now, where are the program segments? So here, this is... Oh, we don't see the execute bit here. Oh, we should fix that. Even though on x86 we don't actually have a way to prevent execution of particular pages, we should still probably note that we are tracking it. Anyway, that's an entirely different issue. Or are we perhaps already exposing this? Proc all. Or what's the program we want to look at? So the audio menu applet, proc 8. Look at the VM. ELF alloc ELF map rx. So we see that it's writable, readable, but we don't see executable. Yeah, we should definitely expose that. But anyway, this is so simple. So just turn on the bit, and then in the page fault handler, when we read from an inode, we quick map the page instead of mapping it into the process address space immediately. We just map it a secret kernel address, do the memcopy there, and then we map it potentially read-only into the process address space. So it's never writable in the process address space unless that's how it's actually mapped. It's really neat. And I don't know, I'm just so surprised with how easy this was. I was building this up, but it was going to be a big task in my head. WP bit to catch invalid writes in ring 0. This bit turns setting this bit will cause the CPU to generate a page fault when writing to read-only memory, even if we're executing in ring 0 kernel. Now kernel in ring, even if we're executing in the kernel. And the only change, seemingly the only change needed to make this work was to have the inode page fault, inode fault handler file back to page, or inode page fault handler, inode backed page fault handler. Use a temporary mapping for writing the read from disk data into the the newly allocated memory, newly allocated physical page. We never note that we never use incorrect, or no, well, that's okay. That's so neat. So fine, let's go and fix up that. I want to see the executable flag. So does region know that he's executable? Is executable, okay. So we're not making the most use of that flag, tell you what. But maybe something is. Well, it's showing it in a few places. We can show it in the proc.fs, so it is readable. Let's just add it here. Region object add executable. Executable, okay. So now we're showing that in the proc.pid.vm files, and then in the process memory map widget here in the system monitor, we can just add it to the list of letters that mean something. So if we have the executable thing, then we will append in X to the little string in the access field in the process memory map in the system monitor. I think that's gonna be okay. Let's just see what it looks like momentarily after we enjoy this very fancy incremental build. I don't know if that was actually an incremental build. I did a make all. Maybe that rebuilds everything now that I think about it. I guess that it did. It was just a C-cache build. Anyway, it was nice and fast. Fast enough for me. So let's see the system monitor. Show me Windows Server. Okay, so we see that here, nothing here is executable all the way down until here. This guy has the X bit, and now we can see it. So once we do a port to 64-bit, like x86 64, then we'll be able to actually enforce this bit, which will be really nice. Right now, we are a little bit held back by the missing NX bit in x86. But we'll get there. So still plenty of things to hash out before we have to make that port. But today's work, very nice little progress, I would say, on just general kernel goodness and enforcement, or hardware enforcement of correctness, which is something that is very good. So kernel expose region executable bit in proc.pid.vm. Also show it in system monitors process memory map u as x tables. Okay, so I think this is going to be it for today's video. So if you made it this far, then I thank you for watching and for hanging out while I go through the surprisingly easy process of enabling the write protect bit so that the kernel can no longer write to read-only memory. I'm still kind of expecting it to just super crash and fall apart, but it seems like it's not going to happen right now, so that's really cool. And here's our executable bit right here. So yeah, thank you everyone for hanging out, and Merry Christmas, and I will see you next time. Bye.